Welcome. Today I'm going to talk about how to deal with missing data, which is a common problem whenever we want to analyze a dataset, and also something to think about when reading published research. Why does missing data matter? Well, basically all standard statistical tests assume that the data that we have is a random subset of the data in the entire population. Whenever we have missing data, that's no longer very likely. And of course also, missing data just means that we have less data, so we quickly have less statistical power. So what to do about that? Well, the first is really to check whether there is missing data, then to think about why there is that missing data, whether it's likely to cause problems, and then look at a couple of strategies for dealing with it. Why might data be missing? Well, there are three main reasons. The first one is so-called unit non-response. It's quite straightforward. Some people that we would like to involve into our research might just be less likely to participate than others. Classical example in survey research is that likely people who have more time at their hands, who might be unemployed, who might be retired, maybe they're more likely to participate than someone who has a very busy, stressful life. In that case, we would have unit non-response in the sense that younger, employed people might be less likely to participate, which might become a problem. The other type, which I'm mostly focusing on right now because it has been shown to be the more problematic one, is item non-response, which is either caused by respondents saying, well, I don't want to share that. If you do a survey on sexual preferences, participants might, for a couple of questions, say, I don't want to answer that. Or a related reason, participants might make mistakes, might give answers that are invalid, or might give answers that you can't interpret within the coding scheme that you have chosen. In any of those cases, we will not have a data point for that particular item, for that particular participant. And kind of a combination of the two is dropout. It's all about participants who start in your study and then don't complete it. So in longitudinal studies, that's quite an obvious problem. If I study some health intervention over a couple of years, some participants will move away, might die, might get tired of it, might change their contact details so they can't contact them anymore, so they might drop out at some point. However, that can also be the case in a simple questionnaire. Participants might lose internet connection or might decide that they are done, that they are bored, so they might stop answering halfway through. Those cases are a combined situation of unit non-response and item non-response, and are just something to be quite mindful of, particularly in the case of longitudinal data. So what do we do about missing data? The most common procedure, and what we've used in this course so far, is case deletion. So just means we delete the cases where we don't have data, we don't consider them in the analysis. There are two different ways of doing that. So-called list-wise deletion, which means we look at our data in the beginning and delete everyone from the list of participants who doesn't provide complete answers to the variables of interest. The other option is pairwise deletion, where for any one analysis, we delete participants who don't provide the data for that particular analysis. And that's the standard in R. Either because functions do it automatically, all plotting functions, for example, tend to do this automatically, or because it's what happens when we set na.rm to true. Case deletion is very, very commonly used. In this, by now rather old review, they found that 94% of papers actually used forms of case deletion. But in fact, it is quite problematic. We'll get to why in a moment, because in order to understand why it is so problematic, we need to think about different types of missingness. The first option is the so-called MCAR, where data is missing completely at random And that means missingness is not related to any variable in the study, and it's not related to the value of the missing variable. For example, this might be when I invite participants for a follow-up study and a couple of invitations randomly get lost. In that case, the fact that they didn't show up is only related to random chance outside of any of the variables of interest. An alternative is that it's missing at random, which means that it might be related to other variables, but not to the value of that variable that is missing. So that some participants might be less willing to answer a question about their sexual preferences, might be predicted by their gender, might be predicted by their age, but crucially, it cannot be predicted by the answer that they are not giving to us. If that's the case, we say the data is missing at random. Otherwise, the data is missing not at random, which means that the fact that the data item is missing is related to the value that variable has for the participant. So it might be that people don't want to report certain racist attitudes, so that if they score high on these attitudes, they're more likely to refuse answering to that particular question. That's the most difficult type of data, of missingness to deal with. And in fact, the most honest way of dealing with that is to limit our analysis quite explicitly to the people who are willing to answer, and then to report out of the people who are willing to talk about their political orientation, the following associations emerge. So how do we figure out what type of missingness we are dealing with for a particular variable in our data? The first thing to think about is whether the data is missing not at random. And that's something we can't immediately test with the data that we see. One thing we might want to do is to just think how likely it is that for that particular variable, whether or not participants respond might be linked to the value that variable has for them. We might specifically try to get data from a couple of participants who initially haven't responded, and then try to see whether those participants have a different value in the variable than participants who initially responded. And a very much related thing that's often used in survey research is to compare participants who readily agreed to provide their data to participants who were harder to reach and who took more effort to be convinced. Because then the argument is that if a participant needed to be contacted 5 times, they are closer to missingness than the participant who participated the first time they were contacted. In general, given that it's very hard to deal with data that's missing not at random, we try to assume that it's not missing not at random. It's an assumption that needs to be justified. It's not an assumption that needs to be 100% correct. Some association there is fine in most circumstances. But if you have strong reason to believe, empirically or logically, that the data is missing not at random, you need to report that, and as I said, restrict your analysis just to the participants who are willing to respond. When we're then thinking whether the data is missing at random or completely at random, we're now able to employ statistical tests, because the difference between those two is whether missingness is related to other variables I have observed. So, the long manual way would be to have a dummy variable for missingness and see whether that's related to any of my other variables. In the case of sexual preferences, I could have a dummy coded 0-1 variable for whether or not that item was refused, and see whether that's related to gender, whether that's related to age, and so on. I can also run the so-called Little's MCAR test, which pretty much does that test across all of my variables. In R, there's the Euler-Etzig package that you can use to run the test, and if the test is not significant, then we can assume that the data is missing completely at random. If either the test is significant, or you find significant associations between missingness and other variables, the data is not missing completely at random, so that we would typically assume that it's so-called missing at random. So with this in mind, the different types of missingness, let's go back to the question of what to do about missing data. So case deletion is problematic because unless the data is missing completely at random, it introduces bias. Unless the data is missing completely at random, our dataset for analysis after we have made the deletions is no longer representative of the population. Once more, in the case of sexual preferences, if older people are less likely to answer to that question, and I just delete those cases from my dataset, my sample is no longer representative in terms of age. So I have a problem here. Regardless of that, this approach always throws away information, even if the data is missing completely at random, and still losing valuable information. It's a very simple approach, so it's often used, and it can be a reasonable choice if the data is missing completely at random and not too many cases have missing data. It's important to think about cases here because we're deleting participants. So if I have 10 variables in my study and each of those variables just has 2 or 3% of missing cases, that can still add up. That might still lead me to up to 30% of participants having at least one missing value. If I then delete them, my sample becomes very small. And then when it comes to this question whether we do listwise or pairwise deletion, quite often people recommend listwise deletion because that's the only way to use the same dataset for all my analyses in a paper, in an assignment. Of course, to be able to do that, you need to filter the dataset so that you only have relevant variables in there, because you don't want to exclude participants who didn't answer a variable that you're not even looking at. And then you can use the NA omit function in R to drop all lines that have at least one missing value. Another approach that often comes in the next step is to reweight the data. We've already seen that for unit non-response. So if I get very few younger people in my survey about voting intentions, I might give them a higher weight. I can of course also do that based on deleted cases. If I end up deleting a lot of older people from my sexual preference survey, I might give the remaining ones a higher weight. However, that's quite difficult to do when I have lots of variables with a couple of missing cases. And it's generally something that requires quite advanced statistical knowledge. So the one place where we are likely to encounter it in the kind of data we want to analyze, so we're looking at large-scale surveys that often have survey weights, and they are generally, among other things, including these two parts of information. So that's the strategy of reweighting data. The most powerful strategy for dealing with missing data is imputation. And that's just about filling in the blanks with some meaningful values, with our best guess for what that value should have been. And a couple of simple ideas that are actually used somewhat frequently, but they're clearly bad ideas. So one would be mean imputation. So I say, well, any missing value, I just replace with the mean of that variable. or for that matter, the median. Why is that a bad idea? Well, because it doesn't reflect what's going on in the data generation process. So in this example here, I have a very clear shape to my data, a clear logarithmic or rather exponential relationship. And then when I add some random means in the place of missing data, I get a second pattern, I get an additional straight line. Doesn't make much sense. So what should we do for imputation? Well, we should try to find a way of modeling the missing data with some kind of conditional mean imputation. So we try to replace missing values with our prediction for what that particular missing value should have been like. Quite an easy way of doing that is to use a regression. There are more complicated ways, and of course for categorical data we can't use the regression, and then there are various more advanced sort of machine learning approaches like decision trees. Don't need to understand them, you might want to use the applied functions at some point. But let's consider a full example of missing data and have a look in the video description for a link to this full work example with the full code. But let's say we're testing a mentoring intervention where we test students at 2 time points, and in between those 2 time points they experience some mentoring. And let's say our main question is whether the effect of the intervention differs between boys and girls. So this might be a small snapshot of some of our observations. And we can see a couple of lines have missing data. So if we now want to figure out what the impact of case deletion is, we need to know a bit more about our data. So let's just make three assumptions. So let's say without our mentoring, boys perform worse than girls, which is true in many school subjects. Let's assume everyone benefits from mentoring in the same way, and they get on average a 15 percentage point increase in their grade. So that's what we want to find. But let's also assume that missingness is caused by a very simple effect, which is that students who fail the first test don't return for the second test. And now in the real world this might be probabilistic, so more of those students might not return because they're demotivated and don't want anything to do with this program anymore. Or it might actually be rules-based. They fail, they have to leave the course. In any case, it's a realistic thing that could happen in research. What's the pattern of missingness here? Well, it's missing at random. Not completely at random, because we have a variable in our data that predicts missingness. That variable is the first test score. It's not missing not at random, because the second test score doesn't influence missingness. At least not beyond the relationship it might have to the first test score. If we now don't really think about missing data, do case-wise deletion, we'll see that under these assumptions, girls end up performing or experiencing a greater impact of the mentoring program than boys. It's not clear to you why that is. Actually do have a look at the link in the video description. It's basically a case of regression to the mean. But we get a result that does not reflect what we know is going on in the simulated data. So very clear suggestion that case deletion in this case is a really bad idea. So we do want to do imputation. Whenever we do imputation, we want to make sure that we keep track of which values were missing in the beginning. If we don't do that, we won't be able to be transparent, and we won't be able to see whether our imputation has changed our results. To do that, we will be using the naniar package, And just as an aside, the naniar package is very helpful in exploring missingness overall. So when you get a new dataset, a good thing to do would be to run the summary functions from the naniar package to learn more about missingness. So misvar summary, for example, tells you for each of your variables how much missing data you have. But for our purpose just now, to keep track of which data was missing before imputation, we need two other functions. The first one is bind shadow. And what that does is, it takes each of our columns and adds an additional column that just shows whether the value is missing or not. So if we have a data set with 5 columns that each have missing variables, we now get a data set with 10 columns, the 5 initial ones, and 5 new ones, basically a dummy variable indicating missingness. And then we also have the function add label missing, which then adds one more column that just indicates whether there was any missing data in that line to begin with. So those two functions are functions we generally want to run on our data before we start with any imputations. Let's have a look what these functions do to the example dataset. So the first one, bind shadow, adds a column for each column that had missing data before. In this case, it's only one, score 2, so it adds the column score 2 NA that shows whether originally that data is missing NA or not missing, not NA. Add label missing adds another column that now indicates whether there's any missing data across the row. Of course, in this particular case, the two columns are redundant, but usually we will have more than one column that has missing data. Now to the actual aim. What we wanted to do is we wanted to impute the values for score 2. So we want to fill in the blanks with meaningful values. How do we do that? So we use the impute lm function from the simputation package. The simputation package is a package that has lots of functions for imputing data with various methods, but let's keep it simple, use a linear model. We want to add a random residual to our imputed values. And that's important because if we don't do it, we start introducing bias. I'll get back to that in a moment. And then our function would look like this. So we do exactly what we did before. We bind shadow. We add the label for missing. And then we group by gender because we expect that the effect might be different by gender. And then we run a linear imputation, predicting score 2 by score 1, and say add residuals observed. So, back to the residuals. If we don't add residuals, what we're doing is we're calculating the regression line, and we're imputing data that falls exactly onto the regression line. If we do that, and then go back later on and test the fit of the regression line, of course the fit is artificially good, because we have placed a couple of points right on the line. It's not something we want to do, because then the testing further down the line becomes meaningless. Instead, we want to calculate the regression line and impute values that are as close to the regression line as the values we observe. And that's just what we're doing here with the add residual observed. What it does is it picks one of the residuals and adds it to the predicted value. That just keeps the size of the residuals, the average size of the residuals intact. We can see that it's now imputed 2 new values in the places that used to be NA, and the 2 functions, the 2 columns we added with the naniar package, they help us to identify them later on. It's important to identify them later on because we need to check that the imputed values are plausible, and we will want to check whether they are influential, whether they make a difference. And an easy way to check it is by coloring them, individualization, using the additional columns. So here I'm now plotting two box plots of the change scores for boys and girls. And I'm coloring the points based on whether any data was missing at the start. So all the orange dots are the imputed ones, all the blue dots are the ones that were there initially. The two main things we can see. One is that the orange dots are generally plausible. They're not outside of the range of the blue dots. So there's nothing to indicate that any of the imputed values are impossible. And we can also see that they're clearly influential because their distribution is different from the distribution of the blue dots. Now, with the imputed values, we would reach the conclusion that there is no difference in the impact of our mentoring program on the two groups, which in this case, since we simulated the data that way, is the correct conclusion. We could take this one step further by running multiple imputation. Because having missing data adds uncertainty to our data. And what we have done so far is just to find a way to not exacerbate that. So if we just delete cases, we make the uncertainty, we make the problem in our values bigger. If we impute them, we try to keep it stable. However, we might want to account explicitly for that uncertainty. And the way to do that is to run the imputation multiple times using something like the random residuals that we added here already. And then see how our statistical conclusions, our statistical models differ across these multiple imputations. You will not need to do that in the context of this course, but you might want to just know conceptually what it is when you encounter it in the literature. If you ever want to do it in R, the mice package makes it reasonably accessible. But what to remember from here? The first point just is that missing data matters. It can bias results, so it can lead us to wrong conclusions, and if left untreated, it reduces statistical power and makes it less likely that we detect effects that are really there. In order to deal with it, we need to consider why it is missing. There are three possibilities. One is it's missing completely at random. So whether or not it's missing is determined by variables that are just not there in our study, that we're not interested in. It might be missing at random, which means that missingness is predicted by other variables in our study, but not by the missing variable. Or finally, not at random, which is when the value that we're not seeing is related to the missingness. That's the most problematic case. Case deletion is only acceptable when we can assume that the data is missing completely at random. Otherwise, case deletion leads us, or can lead us to the wrong conclusion. And we really should do imputation. And we don't want imputation to lead to data that gives us false confidence in our estimates. So we need to add random residuals in the imputation. We practice it in class, and as I said before, there is a link in the description of the video that goes through the full example here with some additional explanations and the full R code. So thanks for watching, and I'll see you in class.